So today we're going to talk about ATG modeling using the PFC. So based on Guru's lecture yesterday, I think we all have a very good idea how the free surface is going to behave if the solid is subject to certain strain, right? So I'm going to talk about two scenarios using the PFC to model the stress-induced instability. So first case will be the solid-liquid surfaces, right? So in PFC, you can set up just a solid-liquid coexistence, then try to press your solid and see what's going to happen on the planar surface. And the other is the solid-solid surface, which means a grain boundary. So as just introduced by Guru yesterday, that we are expecting if two solids, there's no difference in its elastic behavior, then we don't expect the planar surface to become like a wavy profile, right? So we are going to test that classic prediction and see what would happen when we compress our solid in a PFC. All right. So before I move on, I would like to mention there have been several works focusing on this ATG kind of instability. So Zifang Huang has done a very good job, especially using the amplitude equation to model the ATG, and also, as always, there's a lot of detailed analysis on the physical phenomena. So I will strongly recommend you to read Zifang Huang's paper. But today, mainly, I will talk about our work back in 2009. So let's get started. All right, so as introduced by Guru yesterday, there's a lot of experimental data that supports to show that you are expecting to see the planar surface become undulate if the solid is subject to certain strain. So it is a very old experiment. They are showing that for the silicon germanium film growing on a silicon substrate, you are expecting to see this kind of undulation occurring itself. So a very simple physical picture behind that is that since the film is like a silicon germanium alloy and it's deposited on a pure silicon, so you are expecting there is a lattice mismatch between the substrate and the film, right? So in this case, just for illustration, I'm assuming that the film, its lattice spacing is a little bit wider, larger than the lattice spacing for the substrate, right? So you can see that difference. And because we just start to deposit the silicon germanium atoms on the substrate, so during deposition, there will be a very nice coherent surface occurring on the film substrate surface. So we are expecting to see the silicon germanium is going to align well near the substrate. So in a sense, the film, the lattice spacing is forced to be constrained, right? So that they can have a very nice coherent surface here. So as the film grows, you can expect that there will be strain energy being stored in this film, because if there's no strain, the film would prefer a larger lattice spacing, but due to that constraint, everywhere for the film is going to have strain energy here. So you are going to expect that as the film, the thickness become larger and larger, there'll be more and more elastic energy stored in the film, right? And to a certain point, the energy will be too large. And if there is a small undulation on the surface, like this, so what's going to happen next is if there is small undulation on the surface, if you watch what happened on the peak of this undulation, is that there is no other atoms there is no lattice plane nearby top of this undulation. So which means the lattice plane of the film can expand freely toward its free lattice parameter, right? So it's like a fan, just like spread out a fan. You can see all the lattice plane being spread out a little bit. But due to that effect, you are expecting the lattice spacing around the trough is being compressed more, right? But if you do the calculation, just like what we did yesterday, you are going to find out this kind of surface undulation, the total free energy of the system actually is going to be lower than the planar interface. So although there is part of the film, the elastic energy become lower and some part of the energy become higher, but overall speaking, when you carry out a calculation, you can show that the free energy of the system is going to be lower than the planar surface, all right? Or in other words, you can say that since we are expecting a higher elastic energy, right, at the trough, and a less elastic energy at the peak. So that will give you a chemical potential difference that will drive the particle flow from the trough to the peak. So if there's a tiny perturbation, you are expecting this kind of instability, which means the atom is going to flow from the trough to the top. If the driving mechanism mainly is a surface diffusion, but if that kind of mechanism has been established, you are expecting to have a larger and larger or higher and higher the peak, and the trough will be deepened because the atom has been moved from the trough to the peak. So once the amplitude being amplified, and that advantage of moving the atoms from trough to peak is going to be enhanced. So you are getting larger and larger the energy difference. So that's what we call this is instability. All right. So that's a very intuitive picture to explain how the ATG occurs. So using that idea, or if you just review what Guru has been showing you yesterday, you know that the energy change of the system is going to be associated with two physical quantities, right? One is the surface energy, gamma, and the other is the elastic energy difference between the planar surface and the wavy surface, right? So if you do the calculation, you are going to have this kind of picture, right? So I'm putting a negative sign, which means if you got something higher, which means they prefer to have a wavy profile, all right? And we are expecting that for a smaller wavelength or larger wave number, and the surface energy is going to be the stabilizing force, because the system, they don't want to have too much surface, because more surface, which means energetically that you will have more surface energy. So they don't prefer that too. Okay, so from this picture, you are expecting there is a band of the wave number. It can be excited for this kind of ATG instability, all right? Okay, so then think about what we have been discussing about the PFC is that we know the PFC would have a realistic solid-liquid interfacial energy, right? So you are expecting the surface property, like surface energy behavior for this model PFC, they can properly capture that feature. And we also showed that the linear elasticity is also be properly described in the PFC model. So straightforward, you can think maybe PFC is an ideal tool to study this kind of solid-liquid surface, and when the solid is subject to some strain, what's going to happen on the surface, okay? Okay, so let me show you one more experiment. It's basically, they are taking an image to show you that the surface profile is going to evolve over time. So in the very early age, the profile is pretty much like a sinusoidal wave. But as time progresses, as the amplitude being amplified, you are going to see an asymmetric profile between the peak and between the trough. You are going to see a much wider and broader peak, but for the trough, it's going to be very, very localized. The curvature is bigger, and in the end, there could be some defects nucleate the trough, all right? Okay, so we have done some analysis, but today I'm going mainly to show you what's the PFC simulation look like and what's the parameter we use for this PFC simulation, all right? So you can set up here like a 2D hexagonal lattice, and first you can set up a stress-free solid-liquid coexistent system, right? And once you have set up that system, now you can just say the system dimension in the x direction is reduced by 2%. So that's roughly corresponding to a 2% compression of your system. So everything so we are using a periodic boundary condition, so there's no problem for, like, in the beginning you have a stress-free solid. But just when you start to run a simulation, you change the system dimension, which means if you are running a spectral code, the corresponding K value will be different. You have to use the modified or the reduced dimension, let's say that's Lx prime, and that will give you a new set of the wave number. And if you're using that setup, the solid here immediately become a stress solid, right? Because the corresponding wave number would not be equal to 1. So they're going to feel the solid is being stressed. Okay, so what we are expecting, although before I was showing you the experimental data, but using that idea that there's a competition between the surface energy and the elastic energy, Spencer, Voorhees, and Davies, they have also run a simulation to see what's expected to be happening using sort of a mean field theory. So you can see for different lattice spacing, but if we just compress the solid by like 0.1 unit of that. So if the initial lattice spacing is 3.9, and relatively speaking, a 0.1 reduction in length will be relatively considered to be a smaller strain. On the contrary, if the lattice spacing is 3.5, and by reduction of 0.1 is relatively speaking a larger stress, you can see an equilibrium profile would be quite different, right? So larger stress, you are expecting to have a rather sharp cusp at the trough. So here we are using the 2% compression, and let's see the simulation here. So usually I would suggest that you should actually weight your system in the very beginning to reach the solid-liquid equilibrium, like compress your solid. But that's going to give you a rather really flat interface, right? And from that configuration, usually the instability is that you will need a small perturbation on the surface in order to see that perturbation to grow. So if everything just being really flat, you have to really wait for a long time and wait for example, like a numerical noise to kick in, and you start to see that undulation. So instead of doing that, what we are doing here is actually sort of give a sinusoidal surface, but the solid-liquid interface is not at equilibrium. As you can see, there's no density wave across the solid-liquid. Basically, just that half of the system is solid and the other half will be liquid, but there is a small perturbation on the surface. So that's why you are going to see in the very beginning the surface is going to move because the system is a little bit far away from its equilibrium. But after a while, you are going to see the system roughly reach the equilibrium and the surface profile is going to show here. Right, so that's the result for 2%. So you start to see the feature that you have a broader peak and also a little bit asymmetric profile, right? So you have a rather sharper trough here, right? So that's the result for 2% compression. And corresponding to this growth rate curve, roughly we are picking the wave number is somewhere with a very smaller growth rate. Okay. So clearly, if we just change the system size, so the way we set up the system is actually we can control Lx, right? So 2 pi over that will be this wave number, okay? So next what we can do is we can expand a little bit the system size, right, to somewhere here. Okay, so now you are expecting a stronger driving force, right? And in that case, you are expecting the surface profile is going to be sharper and sharper. Yeah, so you see a much more pronounced feature predicted by either by the theoretical model or in some similar phenomena you have also seen in experiments, right? But still here, you will have a stable surface profile, but with something really like a cusp occurring here. So further, so basically you can do several different things. You can either move around the change the wavelengths to see a stronger wavelength will correspond to a stronger driving force from the elasticity. So that's one thing you can do. But the other thing you can try is just fix the wavelengths and just start to keep increasing the strain. So you are expecting similar behavior, how the surface profile is going to change. You have a rather sharper and sharper trough occurring when the elastic driving force become larger and larger. Okay, so if we further move to, for example, this one is close to the maximum growth rate, so means which there's a really large driving force for the system. So you are going to see not only the trough become very, very sharp, but there is also a dislocation nuclei at the trough. And the idea is being that, so that just play a very slow motion of that. So what I'm showing here on the left is the density profile, right? But sometimes it's not that easy to pinpoint where is the dislocation. So instead, something you can further do is to calculate the local free energy density, right? But as you know, if I just plot not the mean density, just the local energy density, you are going to see also an oscillatory profile. So you have to do some proper average over one unit cell. So there are several ways you can do that. You can use this FIR filter. But I think back then, the way I did this is to pinpoint the atomic position and just take a certain position. You take hexagons to do a local average. And the idea is that if I pinpoint one certain atom, then using the spectral method, I can recover whatever position it is. I can recover what's the extrapolate density. So in theory, I can have a very accurate what's the density over the space. So I can take whatever average I would like to. All right. So let's watch that closely again. So here is the same simulation, but it's being played, I think maybe 50 times slower. So clearly you can see what happened here is because we know there's an expansion on the top, but a larger expansion it is, the more compression you are going to get at the trough. So when the lattice plane is going to be compressed too much, right? And the goal is to reduce the elastic energy as efficient as possible. So instead of being compressed, either further being compressed, the system at a certain point is going to nucleate a dislocation. And once that happens, okay, so the meaning of this, one of the dislocation is occurring at some place. As we just showed a few days ago, you are expecting, if you see one edge dislocation, then you are expecting above that edge dislocation and below that, there would be a one lattice plane missing, right? So here, the system actually what they did is by forming that dislocation, and you are going to see that there will be one extra lattice plane below, right? Because already you probably have a 30, 40 lattice plane already, and you compress the system. But once that edge dislocation is nucleated there, and once it's forming and propagate, you are expecting above that dislocation, if you count how many lattice plane you are having there, you are going to have one less than what you have below. So now, by forming that dislocation, because if you count the lattice spacing, you will have one less lattice plane above. So which means by forming that, you are releasing the elastic energy above that dislocation. And the dislocation is going to come downwards, right? Because once it goes by, it can reduce the number of lattice plane above. So that's a very efficient way for the system to get rid of the elastic energy. So from this stage, you are expecting to see all this plasticity, dislocation forming and coming, going, things like here. All right. So something that's actually we are expecting to see, right? Because to a certain extent, if you really compress really hard on your material, you are expecting to see a lot of dislocation nuclei in your material. Yeah, and they are going to react and combine and to further reduce the elastic energy of your system. Okay? So here, I'm going to show you the other simulation. That's not in our paper, but just for fun, you can do this kind of simulation. So of course, we have a much larger compression, like 3% is relative high compression. And in our simulation, we have a two solid liquid interface. So I have, so here is already the mean free energy plot. So on the top, there's the liquid phase. At the bottom is also liquid phase because we are using a periodic bounding condition. And center is a solid. And here's the mean density plot. So it's much easier to see the formation of dislocation. So if you really have a larger strength driving the solid, you are going to see a more dynamic behavior. So you are going to see, for example, here you are expecting a dislocation forming at the trough here, right? And also, on the other side of surface, you can have same thing happen. But in this case, because of this dislocation is passing by, so as we just described, as the dislocation is passing by, it's going to effectively removing one of the extra plane, right? So you still have, if there's more time for this dislocation to propagate to the other side, then maybe you are expecting a dislocation forming here. And depends on the sign of the Burgers factor, they might come together and combine and get annihilated. Right? So that's actually the next simulation. So if we just crank up the compression, so here you actually see, immediately you will get the dislocation forming at two troughs. And if you look closely, you can see when those two dislocations get annihilated, there's like a ring structure coming out, right? So that's the elastic wave coming out. And since we now have 4% of compression, so just getting rid of like few lattice plane is not enough. That's why you continue to see the third dislocation forming. But once you have all the, enough number of lattice plane being removed from your solid, then relative speaking, there's very small strength left in the system. That's why in the end, you are seeing this rather planar interface forming in the system. Okay, so here is just give you some idea what you can do with the phase field crystal. The concept is that we know the PFC can capture the elasticity well, so the system can reach the local mechanical equilibrium at the time scale of the diffusive time scale. And the other thing is the system also capture sort of realistic solid liquid interface. So based on those two properties, you can choose proper material problem to work on. So ATG is one of them. All right. Okay, so we further verify, just like Guru talked about yesterday, you can theoretically to solve what's the stress field, strain field for this stress solid. So just to verify the system actually reached the mechanical equilibrium at all time. So just during the evolution, we just pick certain time step. Then we just calculate the strain field along the line across the peak, okay? And in this simulation, we actually have a rather extended solid, right? We don't want there is an interaction between the top surface and bottom surface. So by the technique we introduced earlier, you can pinpoint accurately the location of atoms. So from there, you can easily calculate the strain field. And also you can derive, just like yesterday, what's the corresponding elastic strain field if there is undulation on the surface. So we make the comparison. You barely see the difference between the classical theory and the dots basically is the measurement from the phase field crystal. All right, so it's very good agreement. So we measure the strain in the x direction and in the y direction, all right? So it's along that line. Okay, so we know there is a good reason for that, why the mechanical equilibrium is reached at all time, because especially when you write down the amplitude equation, you clearly see that the amplitude is behaving, evolving at a time scale that's different than the mean density diffusion process, okay? So there are more results talking about the nonlinear regime. For example, typically we are expecting whether we just apply a compressive or tensile strain to my solid, I am expecting a symmetric behavior, right? Because the elect strain to the lowest order only proportional to the strain square. But if you recall the calculation I have done for the hexagonal lattice, the reason we recover the linear elasticity is that we just truncate the higher order term. But when the stress is high as like 2%, for example, well, you are going to pick up certain nonlinear elasticity, right? Because if the strain is not small enough, you are expecting to see those higher order terms. So if you include those terms, you are going to see a symmetric contribution, which means when you compress or stretch your solid, you are going to pick up slightly the asymmetric response. So I did not put the figure here, but in our paper you can see the response at high strain is going to deviate a little bit. Okay, so we also analyze the profile. But this lecture basically is just to give some idea what you can do with PFC. So here is a 3D simulation. So we just go to a 3-dimension. It's still a solid-liquid coexistence. So whatever on top, that will be a liquid, and in the center will be a BCC solid. All right. Okay. So we apply a biaxial strain, and so the solid is strained. So in order for it to release the elastic energy, we are expecting to see the surface undulate. And you start to see the nano-island formation. And I'm going to play the video again. So if you focus on the area here and the area here, you are going to see a dislocation formation as well. But now you got some idea. Now it's a 3D. So in 3D, you actually can have like edge dislocation and screw dislocation. But of course, in this case, that would be the edge dislocation. So let me play the movie again. So if you focus on the trough, like here, you see, if you really count how many lattice plane you're going to see, the lattice plane below and above that dislocation is going to be different. And something else you can ask is, when you have this biaxial strain, right? So you have this nano-island forming. Is it always going to have this square pattern, or it will be something else occurring here? And here we basically only set up the XY dimension to be like a cube, a square. So it seems like we are forcing the system to go through this square-like patterning, right? But there's something also is of interest to ask: what kind of nano-island patterning you are going to have? If the underlying lattice have this BCC symmetry or FCC symmetry. But here, just to give you some idea, what's going to happen if you stress your solid? You are going to see the surface undulation due to the stress-driven instability. Okay, so next thing is also just a demo, because of course you will see like a silicon germanium film. You have this rather rounded nano-island forming, right? But for different setup, you can also have like temperature is different. You can also have like pyramid formation, which means if you look at the detail of the island, you are getting something like facets. So in a PFC, you can crank up the parameter epsilon, because in the multi-scale analysis, we show that smaller epsilon gives you a diffusive interface. But a larger value of epsilon, you can have a rather sharp interface. So here, I am going to still compress the solid, but crank up the epsilon to a certain larger value. And I also adding a noise. So here is the results of the simulation. So you can see certain feature that the solid-liquid interface is really sharp. And because I'm adding a noise to a system, So sometimes you will get the atom attached and remove that. You can see that step flow. And of course, the system seems to prefer form the facets in this direction. So you are seeing a lot of motion, the atom coming in and out along that surface. But in the end, you are going to expect to see something facets like what they have been showing in experiments. So just, again, give you some idea what PFC can mimic. But I think more importantly is actually to analyze, for example, the strain field in detail, right? Now you have these facets, so you have all these like step ledges and steps, right? So would those like steps and step, the stress field around those corners, where they interact, and how are they going to influence this nano island formation, things like that, right? I think there are some papers they have been doing that, but still, I mean, there's a lot of something we don't understand yet. Okay, so that be my introduction to the phase field crystal modeling of this solid liquid ATG instability. Okay, maybe we can move on to next topic. It's our recent work with Professor Gururajan. We got this result just published this year in Physics Review Materials. So the question we are trying to understand is that, of course, the grain boundary is important. Now we are talking about the solid surface, all right? But just before I start, the slides is prepared by my former student, Mingwei Liu. He's now in the United States pursuing his PhD at UIUC. So he's the first author of this PR material paper. All right. So let's talk about the stress-induced instability, whether that actually exists for this pure material. You have like only a grain boundary separate the same crystal, right? So you have two solids in contact, but those two solids, they are identical solids. There's no elastical inhomogeneity of nearby grain. They are just separated by a grain boundary. So in that case, if we do the similar operation to compress the solid, will there be anything occurring in the system? So, of course, the grain boundary is very important. You can employ to manipulate the grain boundary to achieve certain material properties. So you probably are much more familiar than me. So some examples I'm showing here. So the question we're asking is that it is being shown that if the system is subject to a shear strain, then the grain boundary is going to undulate. That's known. But just like what Guru has talked about yesterday, classical theory predicts that if you have everything the same, you have the same grain, but just to rotate differently, right? So elastically, you have the same stiffness, right? The hardness, everything are the same. It's separated by a grain boundary. Then when you compress the solid, you should not expect to see there's any undulation of the surface. And the reason being that is that you will need a rather softer solid nearby, right? So the harder one can actually bulge into the softer one. And during that process, you can see there's a elastic energy difference due to that wavy profile. But if they are all the same, you're not getting anything from that calculation. So in theory, we are not expecting to see any undulation of this planar grain boundary. Okay, so here just a quick review of ATG, but we're just seeing that solid liquid interface, you compress the solid because now you can consider the liquid phase is have different, let's say the bulk modulus, right? So it's relatively very easy for a solid to bulge into a liquid, right? So in that case, we can consider a solid is in contact with a much softer phase. So in that case, we are expecting to see the surface undulates, and which will lower the energy. And this is the figure I didn't show you before, but that's from 2009 paper. So we also measure different growth rate versus the K under different compression. Okay. And there we show, actually, we can really compare with the classical theory, and the critical wave number here is actually proportional to the Young's modulus and the strength squared divided by the surface area. So everything worked out well, just using the PFC to model the solid liquid ATG instability. All right, so now let me introduce a little bit what's the simulation parameter for this solid-solid simulation. So we're trying to have a rather mobile grain boundary, so which means we don't want to choose our parameter really deep inside the solid region. So we choose the parameter rather close to the solid dust line. So you can see epsilon equal to 0.1, which is the value we use frequently in a tutorial session. And percent bar is like minus 0.196, so that's really close to the solid dust line. So although I have a solid, but the interface is going to be rather smooth and rather mobile, let's say. Okay, so that's the free energy, and that's the evolution equation. We're using a conserved dynamics. And as you know that always we set up system, the one unit cell is like 4 pi, the other would be 4 pi over square root of 3, and things like that, all right? Okay, and we're choosing a rather high angle grain boundary. So here is like a positive, negative 10.8, so which is the second smallest simulation domain that we show in the tutorial session. So the misorientation here is like 21.6 degree, and it's a periodic boundary condition. So actually there will be 2 grain boundary. One is at the center, the other is on the top. But just to avoid the grain boundary interaction, we are making the y dimension rather extended. Okay? And in the following, I'm going to show the simulation is not the density plot. In most cases, I'm showing you the density peak plot. And so and we also color the density peak differently. If the density peak the value is low, like less than 50% of the maximum, then we are marking them like different color. So those basically are the atoms at this location. Okay? So, yep. So what would depends on the length? Right? Oh, right. So that's a very good question. So we are also going to change the length. And why is that? Because according to like previous ATG simulation, if I change my lateral dimension, that corresponding to different wave number of the perturbation of the grain boundary surface. And we know the growth rate usually depends on the wavelengths, right? I mean, if 2 solids, they have different elastic property, then different wavelengths of that surface undulation is going to give me the different elastic energy differences. So yeah, we will also change my lateral dimension just to see for different kind of grain boundary perturbation and whether the grain boundary will remain always stable or sometimes it can become unstable. Do I answer your question? Okay.
So you are trying to keep only one wavelength?
Yes.
Yeah.
I mean, if you do a really extended system, and the advantage of that is that you immediately explore all sorts of wavelengths, right? Because for a shorter wavelength, they can repeat themselves, right? So if you really want to just get a feeling if the grain boundary could be unstable, you can run a really large simulation, and usually you will pick up the most unstable mode immediately. But here, or something we prefer to do is actually to systematically measure the growth rate for different wave number. So depends on your purpose. Usually a larger simulation, of course, is more realistic, right? You immediately pick up different wave number, and sometimes those wave number, they can interact and form a nonlinear profile, for example, things like that. Okay, so let me show you 2 simulations. All right, so if you just run the PFC simulation, and what you are going to see are 2 possible outcomes, actually 3. One is if you don't compress your system hard enough, there's nothing going to happen. But in this case, if we increase the compressive strain to like 0.9%, what you're going to see is that in the very beginning, you have a planar grain boundary surface, and you are going to see the surface undulate a little bit, then stop. Nothing going to happen after a while. So if the strain is really small, you just got a planar surface and nothing going to happen. And that threshold is roughly 0.5%. But here is like 0.9%. So you start to see part of the surface. If you look closely, I probably have that later. So let's move on to that. Okay. So like 0.9% compression. So in the very beginning, you have a rather flat interface. Then at a later stage, if you look at part of the grain boundary, you are going to see a very different structure than what you set up in the very beginning. So if you just let the system being compressed, and they will form a little bit deformation or a little bit undulation. And locally, you can see part of the surface forming by the kite structure. It's like what we set up initially. And for a little bit curved the surface, you are going to see this zigzag structure. It's a little bit more disorder. And a very quick reasoning of that is that the system trying to undulate, but something happened and trying to pull the undulating surface back, right? So the system is kind of being pinged by some force. So that undulation does not keep going and become larger and larger. All right. So that's the first feature. Oh, actually, the second. The first feature is that there's a threshold compression. You have to go beyond 0.5% in order to see this kind of undulation. And the second feature is that even as the compressive strain is increased to like 0.9%, you start to see the undulation, but it's going to be stopped rather quickly and just stay in that configuration. And the third thing is that, so if you crank up the compression like to 1.2%, you are going to see this surface undulation occurring, right? You have this sinusoidal wave. And what's going to happen next is quite symmetric, but I didn't show the lower left part. But you're going to see a dislocation, nucleation, and as we have shown in previous ATG, that's a very efficient way to get rid of the elastic energy, right? But thing is that what is happening here, I mean, in classical theory, we don't expect to see the grain or the surface between an identical solid, right? In that case, even if there's a compression, we are not expecting to see the surface undulating, because by doing so, for a wavy profile, you are not gaining any reduction in the elastic energy or things like that, right? Mm-hmm.
We are considering now a hexagonal lattice.
Oh, right, that's right.
Because of which it is isotropic.
Right.
So differently oriented grains do not have different.
Any difference? Yeah, they will be the same.
To the compressive stress, they are.
They respond. Yeah, they'll be exactly the same.
Now in a cubic system,
mm-hmm.
and if one of the grains is aligned favorably to the compressive stress,
right?
Do you think, because there is an elastic inhomogeneity because of orientation,
mm-hmm.
the Young's modulus of that orientation could be high and another one could be low. So
in that case, you are expecting. Yeah, I would think so. So in that case, something we're expecting is to see the surface undulate, right? Yeah, so something I forgot to mention, but thank you very much, is to point out that we are running a 2D hexagonal lattice. And the property of the 2D hexagonal lattice is that it doesn't matter how you rotate your single crystal. For example, we can set up like a equal, let's say, one of the side of the triangle is parallel to the x-axis. Then you can compress your solid this way, that way. Anyway, you like. You are always going to get the same elastic response because the system is isotropic. So here in 2D, actually, elastic speaking, the upper grain and lower grain, there's no difference, right? So we should not expect to see this kind of undulation or this kind of very clear there's an undulation occurring for this solid-solid system, all right? So, what is happening here? Any guess? What would be the possible reason for this kind of phenomena? I mean, we are not saying that this phenomena can be easily observed or it's always going to be there. I mean, there must be some assumption for this kind of system to be able to be observed, like in MD or in experiments, right? So, a short story is that for this 21 degree, right, the grain boundary, it is a high angle grain boundary. So for this high angle grain boundary, we are seeing that the grain boundary basically is a very relatively disordered structure and rather continuous grain boundary, right? So the thickness or the area of that interface or of the grain boundary is not actually a line. It is an area, right? You have a region we call the grain boundary, especially you see from the simulation or from MD, you actually see the grain boundary is not just a line. It is a region, maybe across one or two atomic layers, but it is a region. So if it is a volume occupying a space and with a slightly or rather disordered structure compared with a solid, then you are expecting it's going to be a rather loose composed atoms, and that region should have a different elasticity compared with solids, right? So you have a solid and solid, but now something in between, what we call the grain boundary, is no longer just a surface with zero thickness. It's actually a volume. So now it's like you should consider your system is composed with three volumes, right? You have a top solid and bottom solid. By the center, it is a thin region, but still the thickness is not negligible. So you have a third phase, right, or third kind of solid in between. And that third kind of solid or grain boundary would have a different elasticity. And now, if you consider that idea, then the system exactly become the question about you have a rather stiff solid, that would be your regular triangle lattice, and a rather softer, in contact with a rather softer solid, which we call the grain boundary. And for that system, of course, the solid now can take the advantage to budge in the grain boundary, right? Because it's a softer region. And because of that, the system can release the elastic energy due to that budge, right? So that actually a softer grain boundary gives rise to this kind of instability. Okay, so that's the short answer for that's responsible for the solid-solid surface instability. But more important is that that's the idea. Actually, we formulate a mean field theory based on those observations. And we have a very nice theory that can go back and examine what is happening at the phase field crystal simulation. So I'm going to talk a little bit about that. But based on Guru's lecture, the whole idea, the competition between the elasticity and surface energy, pretty much you can formulate that mean field theory. But one thing that's really important is that we are seeing a lot of complex dynamics during this grain boundary undulation. For example, we're seeing if you do a very careful measuring about how fast the grain boundary, the amplitude is going to grow over time. Right? Usually we are saying for this kind of wave number, there's a fixed growth rate. If it goes, it will go at a constant rate growing exponentially. But now we are seeing actually the growth rate of the amplitude depends on the amplitude itself. If the amplitude is certain value, you will get certain growth rate. And as the amplitude get larger a little bit, when you measure the growth rate, you got something different. So you actually get something like amplitude-dependent growth rate. And there's a very good reason for that. That's due to the detailed structure of the lattices. Okay, so that's something that we are going to discuss a little bit more later. So just give you a very intuitive physics picture. So something that's quite important is to consider your grain boundary as a softer elastic media. So that's why it is being sandwiched by nearby solid, you are expecting this kind of instability. Okay, so, yep.
Just to connect it to real case scenarios, this is known to happen in geological systems. Right? You have minerals and they have grain boundaries.
Right.
And sometimes the solution, the water gets into the grain boundary region, penetrates into the boundary region and makes it softer. So stressed minerals inside the core generally have cracks from the grain boundary.
Oh, yeah.
And people try to study, and that is similar to what we are seeing here.
Right. Just at a different scale, but yeah.
Except that those are minerals, so they don't form dislocations, but they form
cracks.
At some point.
Right. But I think the mechanism, right. And there is just occurring at different scale. But the idea is similar. You need something softer, different, being sandwiched by solid. Yeah, that's right. Right. And something else, just for this, we called that kind of behavior dislocation emission if the strain. If the strain is really large. Okay. Something I forgot to mention is that we call a region where the grain boundary, when the strain is not that huge, but you still have this kind of curvy surface, and you do see the grain boundary structure is different. We call this region the grain boundary structure transformation. So just from the simulation, we are seeing three different kind of outcome. One is nothing happened if the applied strain is less than 0.5%. But if it's up to over that, but lower than, let's say, 1%, you are getting this grain boundary structure transformation. But for a larger strain, you are going to see this dislocation emission at a later stage. Okay? And here just a snapshot of what was happening at a later stage. So just right before the dislocation emission, we see that the grain boundary is aligned to certain orientation. And if you do the measurement, you are going to see the tangent of that would have corresponding to that. So the slope is 1 over square root of 3. And why the system prefer this direction to form these kind of facets? So that's associated also with the atomistic detail. So we are going to talk about the coincidence site lattice and later, and that's actually is very the slope of this facets boundary is actually closely related to that idea. Okay, so let's go back step by step, right? We are seeing all kinds of crazy stuff. Like in the end, you have this very nonlinear dislocation emission, but that just takes step by step. In the very early age, when the undulation, or let's say the undulation, the amplitude is really, really small, we are still expecting to be able to measure what's the growth rate of those amplitude corresponding to different wave number, right? So let's first check the linear regime, where we should be able to measure the growth rate for the different wave number perturbation, okay? So just to give you more detail, if you want to reproduce the simulation, so here are the expected simulation parameter, or what would be the elastic property of the triangle lattice we are measuring, or the surface energy, or the interfacial stiffness, things like that. I'm putting that here. So if you measure the growth rate, which means you can set up different Lx and just perturb your grain boundary, then you can do a very careful measurement to see how fast the amplitude is growing over time. So very similar to the ATG, but instead we're doing a solid surface. So the results right here. So as you can see here, for different compressive and tensile strain, right? So for example, the top one is the strain at negative 0.3%, that's compressive, and also for positive 0.3% tensile strain. That was the blue line here, or the blue circle and blue cross. You will see the growth rate for any wave number is always negative. So you set up something wavy, you're going to see the amplitude decay to flat. Nothing happened. And we found that, as I just mentioned, there's a critical threshold for the strain. It's roughly around like 0.45 or 0.55. So 0.3 plus minus doesn't matter. It's going to be less than that. So everything just decay to a planar flat interface. But as we increase the strain, we are going to see a certain feature that's similar to the solid liquid case, is that at a larger wave number mode, we are going to see the growth rate is being pulled down, because at a larger wave number, the dominant factor will be the suppression due to the surface energy. So all the way here basically is dominated by this gamma K squared thing, right? Like here. But what's interesting is that we are expecting the behavior for low wave number should come from the elasticity. But clearly you see that for the zero, when the wave number is equal to zero, in contrast to the ATG, the solid liquid result, the growth rate does not start from zero, all right? It's actually, you have a range, depending on the applied strain you are giving. So over certain threshold, like here is like 0.6, you start to see something positive, right? Which means the planar surface will move itself if there's a huge compression, like 0.6, 0.7, 0.9. When the K equal to zero mode, which means there is homogeneous displacement of your surface, you are expecting to see that. So what is happening is that if there's no applied strain, or when the applied strain is small, the system can somehow manage. If you compress it, they don't have to they still feel comfortable, right? For example, if you look at, for a stress-free solid, you roughly can have this kind of kite structure. So if you look at what happened above and below, it's quite symmetric. But if now I start to compress, and the spacing between those structures is going to become closer and closer. But since there's a compression or tensile, doesn't matter, the system is going to feel uncomfortable of that configuration. So the way they compensate of that is they can move around, maybe go above a little bit, so everything will shift a little bit. But the new configuration might lower the elastic energy of the system. But as you can imagine, if the compressive strain is only a little bit, I just compress the system slightly, the system will say, okay, I still prefer this symmetric structure. So they don't bother really to go over a long distance to change the configuration. So that's why we are expecting under certain threshold, the system can still manage with this kind of configuration that remain like symmetric. But once the compressive strain is too large, and maybe the dislocation chord they feel is too closer to each other, now the interface, they are trying to move everything, whole line, homogeneous to some other places. So by doing so, you are expecting to see a configurational change of the whole planar surface, and that somehow will lower the energy. And that's associated with this idea of coincident side plane. So let me see if I can find a figure for that quickly for you. Yeah, right here. All right. So you can think the idea is that now I have a top and bottom grain, right, being rotated symmetrically. So if you only see the blue one and red one here, is basically, if you rotate the grain, how the lattice side should look like. But across the interface, somewhere here, right? So you are going to overlap those two structures, and at certain lattice side, you are going to see the blue one and red one, they are going to share the same lattice side. So that the place you see that side is what we call the coincidence site. All right. So for example, if we just properly set up our bicrystal, the grain boundary actually is this line across the coincident lattice site, because that will make the top and lower grain very, very much symmetric. But if the stress is large, right, the grain boundary can move to somewhere higher and lower. But as you can imagine, the grain bound structure is going to be different. And because now the system is not stress-free anymore, because we apply certain strain to the system. So the system can actually move over to some other places, and they will form a new configuration that corresponding to a lower energy. All right. So that's a rather physics picture of what's happening for this K equal to zero mode. You are not expecting the growth rate is starting to grow from zero, right? Because you can have this structural transformation occurring that lower the energy for you, okay? So here is the detailed measurement for that sigma naught, let's say, right? We call that for wave number equal to 0. If you compress your solid, you start to see the whole grain boundary being moved and form a different structure, for example, like the zigzag structure, for example. Let me see. So the zigzag structure, basically, you can think is when the grain boundary is moved vertically, and the structure can change from a kite to the zigzag. And for a certain large strain applied to the system can release its elastic energy just by changing the grain boundary structure, the arrangement of the atoms. Okay, so here just a detailed measurement for that sigma naught. So below like a positive negative 0.5 compression, you still have this kite structure. So if you start with a zigzag, it's going to move back to a complete symmetric configuration. So the system will become a kite structure. Doesn't matter where you started, because that corresponding to a lower energy state. But if you go beyond like 0.5% compression, the configuration will change from the kite to the zigzag. So over that, you are expecting to see a different grain boundary structure. All right, so that's nothing to do with the wave number we are putting in. Just by compression, the grain boundary can adjust its location because of the atomic detail. Different vertical position will corresponding to different structure, and they will have different energy. So an easy way to comprehend this is that just by forming different grain boundary structure, so there is energy associated with it. And when you compress the solid, the energy increase will be different for those two structures. And for the zigzag structure, actually, the energy for that is lower at a higher strain, but for the kite is higher. So there is an exchange of stability when we apply different strain to the system, okay? All right, so that's the linear part, but the important feature we pick up here is that, of course, we can measure the growth rate for different wave number. But even if there is no any kind of perturbation, just a planar surface, when you compress it, the plane boundary can shift vertically itself, right? And by adjusting the grain boundary structure to the certain places, the system can have a lower energy. So that's the idea here. Of course, you can see that for different wave numbers, right? You can now set up the system with perturbations. You can actually still measure what's the corresponding growth rate for that, right? And now you probably can understand better why for a lower strain like plus minus 0.3, either the compressive or tensile strain applied here, you got always something negative. It's because the system, they don't tend to move, right? Once they undulate, they will from this kite structure to partly zigzag. But zigzag is energy costly if the strain is small. So they don't want to do that. So any fluctuation or perturbation you give in the very beginning, whenever the undulation parts, if you look at local structure, if you have initially that's a zigzag, it's going to come back to the kite because that will be energetically less costly, right? So that's the way you can comprehend that sigma 0. Okay, so now we can talk about a weakly nonlinear regime, which means let's drive the system a little bit more, so it's going to have undulation and going, okay? So there, what's interesting to see here is that, for example, initially we have this planar surface and we put some fluctuation, right? Some perturbation, for example. But as the amplitude grow larger and larger, so for part of the amplitude could go from here and reach here and goes back, for example, right? So the whole, if you just follow that grain boundary trajectory, you will see part of the grain boundary will go over through different part of the coincident side lattice, and some part would go through different things. But as we just established, right, if you have this grain boundary go across different part of this coincident side lattice, the structure will be different. or in a sense that as the grain boundary goes through different part of the y direction in space, it's going to experience the nearby atomic structure is going to be different. And that's roughly, you can think the system when the planar boundary is going vertically, is going to experience a periodic potential, right? Because locally, if it starts with a kite structure, but locally, if you want to move upwards, right? So it could have this structure changing from the kite to zigzag or along the way to other structures. But there's the energy associated with that will be different. So the system, so when the amplitude being amplified, you can think about the grain boundary, the segment is going through different environment along the way. So if you just fix at a certain x direction and just watch that amplitude going up over and over, because the amplitude, suppose we are saying it's growing over time. So that part of grain boundary segment is going through different environment or different coincidence site. So from here, maybe to the next here, it's going to repeat itself. But you can see the structure will be quite different along the way from this point. The amplitude is growing to here, right? So in a sense, a good theoretical model to model this effect is to artificially adding there is a periodic structure along the y direction, and the periodicity should be the same thing as the periodicity of this coincident side lattice along the y direction. Okay, so it's like you are climbing over a landscape, and due to that discrete structure of atoms, you are expecting when you go along the y direction, you are experiencing different landscape. Okay, right. So here just an example. If we are forcing the grain boundary just at a different vertical direction, so we are seeing here is exactly the coincidence side that is marked in black here, right? So if you go over some periodicity, if you once again you are seeing the black site occurring here. So the difference here and here, they are the same because we are using periodic boundary condition. So the kite structure always corresponding to the line that's go across the coincident side lattice. But during the wave, like halfway through, that corresponds to the zigzag structure, right? So that's something sort of like proof that something you can set up for your system and to see what kind of different grain boundary structure the system is going to give you, all right? Okay, so the system basically, theoretically, ideally we can think it's going to go over like this kind of periodic structure along the y direction. So when we measure the growth rate as the amplitude being amplified, so now we are no longer talking about the linear regime. We're talking about the amplitude now, right? Its magnitude is larger than 1. Before you have to really study the perturbation, so amplitude has to be small, or at least like AK has to be small, like just we introduced yesterday. But now let's say the amplitude, the AK is no longer a much smaller number, so you can see a rather pronounced amplitude. So you along the wave, you measure the growth rate versus its amplitude. You are going to see this oscillation, but now with this picture, we can understand this behavior a little bit clear, right? Because when the amplitude grows larger and larger and larger, it's going through this periodic structure. So you are expecting to see this periodicity is exactly should be associated with the periodicity of the coincident side lattice. So if you see the number here, actually it is, right? Because you see the gap, right? It's a 5/4 of Ly0, that's 9/4, so different will be Ly0. So you always see the growth rate will be become speed up a little bit, then slow down. Then there's a rush again and coming down again. But always you see this periodic structure over and over and over. And for low simulation, the endpoint basically here is the where the dislocation emission occur because the amplitude becomes so large. So in the end, you have this dislocation nuclei at the trough and you start to see this dislocation emission. So Clearly, because of this evidence, that's why in our mean field theory, we put in this washable potential to mimic this coincident side lattice plane, all right? And with some derivation, but I'm not going into detail. But if we assume there's a periodic structure occurring in a space, and that periodicity along the y direction depends on the misorientation, right? Because the coincident side lattice, that the periodicity depends on the misorientation. But if you adding that, you do certain derivation, you can actually see the growth rate will depend on the amplitude, like here, right? The sigma is going to become dependent on the amplitude. And you can really recover this very nice result when amplitude is really, really small. Then the sigma naught will goes back to the original, when k equal to 0, that will be your sigma naught. Okay, so here just some ideas. So here you can see the amplitude when it grows, it go across it has to experience the sort of potential periodicity due to the coincident side lattice. Okay. All right. So now with this picture, we can explain why there are three regimes, right? When the compressive strain is too small, then nothing happens below 0.5%. But for example, 0.9%, it's going to undulate a bit, then stop. But beyond that, like 1.2%, we are going to see everything grows, and in the end, we have this dislocation emission. And the reason is that for different compressive strain, we know there's a sigma naught, right? So below that, there's nothing happen. But above 0.5% compressive strain, we are expecting something is going to move, to grow, right? That's my sigma naught. But because this amplitude-dependent oscillating behavior, so suppose I start with sigma 0, but as my amplitude grows, my growth rate will oscillate over the amplitude, right? As it getting bigger and bigger, it's going to be oscillating. But there is a threshold saying, okay, there's a line corresponding to the 0 growth rate. So if you have something, even when the amplitude is small, you have a sigma naught that's positive. Let's say this red line, that's positive, right? But as the amplitude grows, and your amplitude is going to experience this coincident side lattice. So you're trying to climb. So that's why you have this decrease, these drops of this this growth rate. But when it drops to 0, right? And after that will be something negative. But when it hits 0, which means it should not grow anymore. So it becomes stuck. So that explains why we see this kind of a curvy profile, and locally you will see this grain boundary structure transformation. But for really larger strain, right? Even when the amplitude, the growth rate oscillates with the amplitude, but everything is positive. So in that case, you can have the profile keep growing and growing and growing. In the end, it will form dislocation at troughs, and it meets. So I think an important feature actually arises here for the PFC is that because the PFC capture all the atomistic details, the arrangement of atoms. So of course, it captured the coincident side lattice and the corresponding washable potential very nicely. Yeah, so something you should probably also see in MD, because you also have that coincident side lattice for the grain boundary, right? All right, but this is work we have carried out for the phase field crystal. Okay, so the only thing that we haven't explained is this 1/√3, the slope configuration, right? The triangle wave profile. And that can be nicely explained by this coincident side lattice, right? Here, I'm just mapping the two rotated grain, and you can see for that kind of surface tilted by this 1/√3 is actually a plane go across one of the coincident side lattice plane here. You can see they share the same atoms here, marked as black and black and black here. So that's the lower energy state. So that's why, although in the very beginning we are seeing this rather sinusoidal wave, but as the system can explore to the region, they can find the other coincident side lattice plane it's going to align in that direction because the energetically less costly. So again, you are seeing the PFC can capture this CSL property very nicely. So that's why you have you form this triangular wave, and of course you can also, and if you evaluate the strain, you are going to see a very large strain focused at low trough region. So that's why you are seeing this dislocation nucleate and emit at trough. All right. So here you can also make certain estimation and saying when is the largest amplitude you could have before. So largest amplitude after that, you should see this dislocation emission. So the very simple estimation will give us somewhere the amplitude should be like this. And all the simulation we are seeing is roughly close to that amplitude. We are seeing this dislocation emission, right? So here just an estimation of that threshold. Okay, so in the following, it's just our theory, but we have a theory for that, and we also have a PFC simulation. But again, we have 3 different regimes we can have for this grain boundary instability. One is for smaller strain, and there should be nothing happening. But for a larger strain, we start to see a grain boundary structure transformation. And for really large strain, we start to see you have this triangle wavy profile, and you have a dislocation emission in the end. So here's a phase diagram for the applied strain versus the wave number. And all the symbols are the results from the PFC simulation, right? The solid circles means the dislocation emission, and the empty circles means the grain boundary structure transformations, but the profile will stuck at certain places. And the black cross is the stable region, and nothing happens here. And all the curves here we are showing here is from our theory. So let's take a look of the theory that we propose. We have already shown what you are expecting or what we have been seeing in the PFC simulation. So just to quickly sum it up, that here's the phase diagram, right? So for different applied strain, then you can do a PFC simulation to see for what kind of perturbation, different wave numbers perturbation, whether it's going to be stable, so that'll be cross, right? Or you only see the surface undulate a little bit and see a grain boundary structure transformation, that'll be the empty circle. Or you actually see the amplitude grow and in the end have this dislocation emission, right? And the boundaries you are seeing here to separate different regions is actually from our theoretical prediction. So in the following, I'm going to talk about what will be the key ingredient we're putting for our theory. And from there, you can also see the PFC actually capture all these essential physics assumption very well. So our theory, we consider linear elasticity. So the phase boundary will be symmetric, but simulation you indeed will see a slight difference. Yeah, especially when the applied strain is large. Let me talk about the key ingredient we have in the kind of mean field theory, or theory for this solid-solid interface growth, all right? So, of course, the elasticity is important, so we will have a term that describes the elastic strain energy. So that's a very typical the strain stress product thing. And also, there's the interfacial energy, right? But the interfacial energy now is no longer just a certain number, and maybe you think of consider the surface energy anisotropy. You can also include it. But I think most importantly, we are making the surface energy as a function of the interface location as its height, because we know there is an underlying coincident side lattice. So when the grain boundary is located at different height or different y direction, that is also going to give us a different interfacial energy, right? So One important ingredient we're putting here is that instead of just putting the surface energy gamma, we're actually also making the surface energy depend weakly on the y position. And it's going to be a periodic function along the y position, and the periodicity is associated with the coincidence side lattice, the dimension of that. All right, so if you just go along, the boundary, if it just go along the y direction, once it go across coincidence side lattice periodicity, it's going to repeat itself. So this term actually helps us to capture that amplitude-dependent growth rate. All right, so that's important. So on the interface, because now you have to consider soft region, right? Because in order for this stress-induced instability to occur, only consider two solids with completely the same elasticity will not work. So we have a term that basically account for this surface elasticity. So that's a region, and it will has its own like a shear modulus, right? Okay, and we would like to have our mass conserved, so we have a Lagrange multiplier for that, just like Guru has shown us before. So that's the concept. Although there's the details, but I think the most important thing is this interfacial energy that also depends on where the grain boundary location is. All right. Okay, so a little more detail about the solid elasticity, right? So that's something you are expecting, depends on two Lamé constant, lambda and mu. Then, of course, you are expecting taking the functional derivative of your complete free energy with respect to certain parameter will recover certain physics. So just in the solid, when you do that, you will recover the mechanical equilibrium, so that checks out. And also, we are consider the boundary is a soft boundary. So imagine a case where we have this grain boundary being like bulged into certain phase. Then because we know the physics picture in mind is on one side, the local lattice is going to be expand, right? If that's a peak. But on the other side will be like trough to the other solid. So the lattice is going to be compressed. So on one side, you are expecting the displacement going maybe toward the center, the other just going away. So there you are expecting a shear stress, right, acting on the soft boundary. So here we consider this shear energy for the soft boundary. Okay. Then of course, then from there you are expecting the system for the soft boundary to fulfill also the corresponding mechanic, the stress surface condition there. Okay, so here just a schematic plot to show you that if there's undulation, of course, this is a picture I was telling you, you are expecting on one side of the grain boundary, it's going to be compressive, right? All the lattice plane is being, because of this expansion, everything is being like compressed a little bit here, but on the other side will be like a traction, right? Okay. So still, the key ingredient we just introduced before is about elasticity, but now that is considered the surface energy. So the surface energy contains, like here, the interfacial part, right? Those two things. So basically, is those two contributions. That's right. And if you do the functional derivative, in the end, you are going to pick up the coincidence side lattice contribution. So you will have something related to the washable potential. So without the detailed derivation, but just think about what we just described. If the grain boundary is going along the y direction, and because the coincidence side lattice, we are making the grain boundary energy as a function of y, and there's a periodicity, then of course you are expecting the evolution of that amplitude will also depend on that potential, right? And we also consider surface energy. So you will also have this interfacial energy as a stabilizing force here. Okay? So here is our complete theory, and here is a key result. So just saying the amplitude of the grain boundary is going to change over time. And they are like the two key ingredients you can see from the result here. If you see the bottom line first, This is a term that depends on the wave number. So usually we're expecting the growth rate, right? For the ATG will depend on the wave number. So this actually captured that, right? You see there's a suppression or stabilizing force proportional to k squared, and the prefactor is associated with the physical quantity, the surface energy. And second part is the from the elasticity, but you have some modification in the denominator that's associated with our soft boundary, soft property of the interface. But in addition to that, we have something else that's not in the general ATG derivation. You have on the top line here, you have a term that is not depends on the wave number. You only have a term that depends on amplitude. And of course, that's from the washable potential, right? Because when the amplitude is large, go across certain different spatial configuration of the coincident side lattice, it's going to give you different push or different pull. So through derivation, we are showing this kind of Bessel function behavior, right? So it's quite different than the solid liquid case, and we are showing two different contributions. One depends on wave number, that's generally something we expected, because the elastic energy or the surface energy, the difference will depend on the wave number. But there's something depends on the structure, right? It depends on the coincident side lattice structure, and that contribution should only depend on how big the amplitude, or just saying where your interface is, right? What kind of structure it goes through. All right, so that's basically our result, and along the way, I'm showing you already the comparison, for example, the phase diagram. So all the boundary lines are predicted from the theory I just told you, and simulation are those lines. And even our theory predicts the, let's see, the bigger one. Let's show you. Yeah, so we have something simulation, and we also plot along with our prediction. But let me see if I have that somewhere. Yeah, I don't have here, but you can check out our paper. So basically, from our theory, we have a very good agreement, the kinetics, everything, also the phase diagram, right? So I think the conclusion is that it depends on the material problem you are interested in. Then the strength of PFC, of course, is it can model the linear elasticity and also the defect structure, right? And its dynamics properly. And also, if your problem involves like solid liquid interface, and we know the PFC has its roots in the density functional theory of freezing. So from that aspect, you can also model phenomena related to solid liquid interface. So solid-solid, solid liquid, and dislocation, elasticity or plasticity. Yeah, so that would be the strength of the PFC. Okay. All right. So that's conclude the stress-induced surface morphology, what PFC we have been working on.
So if you just take a solid system and deform, are there any deformation conditions for which it will also twin?
That's a good question.
So that is another mode of accommodating plastic.
Yeah, I think so. Actually, in the following, I'm going to show you the two modes where we can get FCC. You can easily get twinning. But we haven't tried to like apply strain to that.
Even with one mode,
right.
in 3D you can get hexagonal lattice.
Right. Yeah. So in that case,
In that also we should see.
I think so. I mean, there's no reason. So basically, the concept is that if you apply the strain, right? So they are going to adjust the position of the atoms. So if it's lower energy, you will just slide and become a twin. So I don't see any problem having a twin boundary in this system.
So
yeah, it should be.
done these things?
That's a good question. I mean, there are many people coming out, there are many papers coming out every year. So I guess some people have done that, but just to what degree they have done that, we can look into that. But 3D calculation nowadays is relative cheaper than before, so I think it's doable.
Hexagonal because it is just one mode.
I mean, yeah, the BCC along the 1-1-1 orientation, right? Yeah, that's right. So let's talk about the two mode. And I think it's a good idea. Let's talk about the theory today. And for tomorrow, probably we can implement the two-mode idea. Maybe you can work on the FCC, things like that. So let's finish the lecture today, and we will do the tutorial tomorrow. Okay, all right. Okay, so in the following, I'm going to talk about if the design structure is something other than BCC in 3D or hexagonal lattice in 2D. For example, if you want to have like diamond cubic structure for silicon, or like a nickel, like a FCC, right, for nickel aluminum. But the current PFC, the simplest PFC, only reproduce like BCC in 3D and hexagons in 2D. So what further we can do to modify the current PFC model to get a different crystal structure, right? So I'm going to talk about basically two different ways. It's about how we can implement more building block for the PFC. The other is about just how to modify the nonlinear interaction. So there are two ways you can get the structure that you wanted. So, okay, let's start it. So there is a very interesting paper back in 1978 by Alexander and McTagg. The title of the paper is "Should All Crystal Be BCC?" So it seems like if we are getting something that is not BCC, it's kind of strange, right? So the paper is about you can formulate a Gibbs-Bernal theory like just we did in the class, right? You can say the free energy is a function. It is a functional of the density variation, the polynomial of that. There should be a dr somewhere. I missed that, right? So if you, for example, if you do the expansion for that ideal term rho log rho, you are expecting to have an infinite series of this delta rho to certain power, right? And the Gibbs-Bernal theory is a simple theory. You are trying to maybe formulate a double wave potential and out of your free energy functional. So we have seen that derivation just by saying if I have a crystal density can be written as like a mean density and plus the sum of certain density waves. So this summation corresponding to your lattice structure. If you're talking about BCC, then the summation should be summing over all this 1, 1, 0 combination. So you can have 1, 1, 0, 1 minus 1, 0, and minus 1, 1, 0, etc., or 0, 1, 1, right? So you are having like a 12 principal receiver lattice vectors there. But for FCC or other structure, the summation should sum over their corresponding principal receiver lattice vector. Then since the basically or the simplest assumption is that the free energy can be expanded as this density variation to a certain power, the polynomial of that. When you carry out this integral, right, we have shown that, for example, if you have this delta rho square, so you have this density wave summation product, then you can pick up any two of them to see whether you can have two density waves summing up give you a zero factor. If yes, then you are going to pick up a contribution. So for example, if we are saying the first Kj is 1, 1, 0, then this Kl should be minus 1, minus 1, 0. So always you have this quadratic contribution. And whether you have all this cubic or quartic contribution, that depends on if you can form a possible combination in the reciprocal space. So for BCC, and here's one example why you will have a non-vanished cubic term is that you can pick out this minus 1, 0, minus 1, right? So I'm taking this is my x, and this is my y, this is my z. So it's minus 1, 0, minus 1 is over here, and plus this 1, 1, 0, and plus again this 0, minus 1, 1. You are getting 0, right? So basically you check out each individual component. Indeed, you can satisfy this condition. So there are several terms that will satisfy this combination. So for BCC, The argument here is that you always have this non-vanished cubic term, and this term is always going to lower the energy for you and create a double well potential. So you might have a question about how do I know this term always contributes something negative, right? So first we know when we write down this free energy functional, the amplitude we are having here should minimize the free energy, right? And if the alpha coefficient is something positive, then you can expect the amplitude we are getting here should be something negative. Why? Because, for example, for BCC, we can have this oscillating solution over space, right? Basically, sum over all the density waves. But if you simply plug in this A become minus A, if you're adding this minus sign, basically you can absorb that into a phase here. So the only difference with plus A and minus A is just shift the origin of your lattice, but you still have a BCC structure. So there's no problems regardless of sign of alpha 3. You always get a sign that will lower the energy for you, right? So if you have this term always contribute negatively, then you can have this kind of free energy form, which says when A is small, the contribution is going up quadratically, so you are having something up. But for intermediate A, you are the middle part has larger contribution, so it's going to decrease that. And when A is really large, it's going to pick up this A to the quartic power. So you have this kind of double well shape. So since you have two minima, then you can have a BCC liquid in coexist, right? So you can have this BCC liquid interface. Or it's the cubic term basically is the reason why we should expect crystal usually have a BCC phase. But clearly that's not the case in nature. So, but if you want to have a nice Ginzburg-Randolph theory,
the argument is that without loss of generality, you can assume this A's to be negative, is it? That's why the cubic term is giving minus.
Right, so basically just by a shift of the origin, and then A can be negative.
If A is positive, you shift it so that it becomes negative.
Right.
So that term will in general not be zero. That is.
Yeah, it will not be zero because the combination of triads, it exists. But the value why it is negative because we want to minimize that. And A always you have two solutions, right? So even in the beginning we are assuming different sign of alpha, it will always pick up the side that minimizes the energy. So that term will minimize the energy. But clear for FCC, that's the principal receiver lattice vector or the +1 combination, ±1 combination. So there is no way you can get the three of these vectors and summing them up equal to 0. Because just looking at, for example, the x component, you always have either 1 or -1, right? So summing three integers, 1 or -1, any combination, you can only have 3, 1, -1, and -3. So you will never have anything that's contribute to the cubic term. So for the FCC, the energy, if we only expand to the quartic term, you can only have the quadratic and the quartic relation, right? And we would like the system to be stable. So alpha 4 is going to be something positive. So there's only one minima at A equal to 0. You won't have anything else. So there are two fixes to make the FCC structure stable, right? So one way is actually trying to reproduce this double well potential by including a 6th order term. So you can have this alpha 2 A squared plus alpha 4 A to the 4th power and plus alpha 6 A to the 6th power. And you have 3 terms. Now you can make alpha 4 less than 0. Then basically you can reproduce double well potential there. So there is some work using this 6th order polynomial for FCC, so you can formulate a Ginzburg-Randolph theory. So that's the first way. You can include more nonlinear terms, so that the system prefer like FCC rather than BCC. The second method is actually to include more modes, right? So, which means here we only consider the principal reciprocal electric factor, but how about something other than 111? So we still consider 111, but maybe I can add in other set, like 111 together with 200. So if I have a 111 and a 200, now I can have 1200, for example, and the other will be minus 11 and minus 1, minus 1, minus 1. And adding everything together, I can have a non-vanished cubic term. So a quick summary is that if I want to get something other than BCC, for example, I can do it in two ways. One is just adding more nonlinear term, which I will give you a short introduction later. First, I would like to talk about the other method is that you can put in more building blocks. Before we only have the principal set. Now you can add in those different kind of blocks. So with that help, I will show you in the next slides. Then you can have a non-vanished cubic term for FCC. So the first method is just using that idea to construct a two-mode PFC. For example, we can include the 200 mode, right? So 200 mode, which means you have actually 6 reciprocal electric factor, right? Plus or minus 200, or 0 plus minus 20, or 00 plus or minus 2. So one example is that you can take maybe here is one very straightforward example. It's 1, 1, 1, 1, minus 1, minus 1. So you see here the y and the z component, they cancel out, right? I have 1 and minus 1 always here. But x component give us 2, cancel out with this a 2 bar 0, 0, right? So just by doing so, and actually by doing this exercise, you notice a lot of combination can give you that. So here's one example. If I start from like origin, if I first go 1, 1, minus 1, 1, 1, 1 bar, right? So I end up with this location. If I'm adding up this 1, minus 1, 1, so the first component will be 2, the next will be 1, but minus 1 will be 0. And third will be also minus 1 plus 1 will be 0. So I'm ending up with this coordinate. By adding up with the third component, that will be minus 200. It indeed goes back to the origin. So it forms a closed triangle in the reciprocal space. So then in this sense, you are expecting the Ginzburg theory would look something like this. Just by 1, 1, 1 alone, you can only pick up the quadratic term and the quartic term. And just by consider the 200 mode, you can also only have the quadratic term and quartic term because you won't be able to have 3 200 to give you a 0 factor sum, right? Because always, if you pick this one is 2, 0, 0, the other one is minus 2, 0, 0, but you still have a third one. So never you can get triads in the reciprocal space. But because of those two, you are picking up this minus A111 squared times A200. So in a sense, if I only go along the 200 direction, it's only a pure quartic function. There's no 111 contribution. The same thing for A111. But now, if they are not both 0, there will be some certain paths can bring you from the 0, 0, which is the liquid state, to the other minimum somewhere here, right? So by adding the second set of building block, like 200 together with 111, now you can have this double L potential. And of course, that will be in a higher dimensional space. And here, just a schematic plot. So that's the idea, just adding more building block. Now you should be able to have this FCC liquid system. Okay, so how do we use that idea in PFC? So the original PFC, we know this kernel Laplacian plus 1, so K not basically is 1, okay? Here should be precise, but anyway, I'm using rho sometime, using precise sometime. Okay, so we somehow show that the one mode approximation this kernel is associated with the structure factor, okay? So we're actually talking about the peak of the structure factor that's corresponding to 111 in order combination. And since we normalize that, saying the magnitude of that equal to 1, so there's a 1/√3 prefactor here. But now we want to include more modes, right, being excited. So the idea before is, of course, this kernel prefer anything that with wave number equal to k0 or wave number the magnitude equal to 1. So in order to encourage other modes in our system, for example, I want something with the magnitude equal to k1, I can simply multiply this Laplacian kernel with this Laplacian plus k1 squared kernel square plus a little shift. If I don't have this R1, now become very trivial, right? If I don't have this R1, the system will prefer two kinds of wave vector with the wave number either equal to k0 or k1. Because if the wave number equal to k0, then when I take a derivative here, I will have minus k0 squared plus k0 squared. So it's going to minimize my energy. And also same thing, it will pick up the density wave with the wave number equal to k1, right? So why do I need this R1? Is that I would like, since I know 111 is the principal reciprocal Lec factor, and that actually gives me a very nice FCC structure. So other than that, the second mode should be like just a supplementary mode that help the system to have this cubic term and lower the energy. Right, but I don't want to, because if I really plot what's the summation of this 200 density wave, it's going to give me a cubic symmetry, just a simple cube lattice. So instead of just setting R1 to 0, I actually can use R1 as a control parameter to say how much I would like to excite the second mode. So that's just one additional control parameter that I can have. Okay? So we have already talked about why we choose the second mode as 200, because it can combine with 111 to give us a closed triangle in a reciprocal space. And we also talk about we can have a one more degree freedom R1, so we can sort of tune how stronger I would like to excite my second mode. So you can see here, for example, if k equal to k0, right, the whole thing disappears, right? So it basically goes back to the first mode. But for k1 mode, right, so if you have density wave with wave number equal to k1, this term vanish, but this one will have this minus k1 squared plus k0 squared. It's just some number and times R1. So total growth rate is no longer only minus epsilon, it has to add something. So that's decrease the growth rate for the second mode. So you can see from here why we put this R1 here as a parameter that I can control the strength of the second mode. Okay, with that simple idea, you can carry out the phase diagram calculation. All right, very straightforward. So with the original PFC, that's the original phase field of crystal free energy functional. And of course, you can calculate the free energy density as a function of the mean density. And here I'm using epsilon equal to 0.3. So you can plot the free energy density for BCC, so that's the green line. And also for liquid, that's the blue line. And you can naively plug in the n size for FCC, do the calculation, that will be the red line. So for all the density you are seeing here is that BCC seems to be the ground state everywhere. So even I zoom in this part, you can see the green curve always has lower energy than the red one, right? Which means BCC is a true ground state, and FCC in this kind of free energy functional always has a higher energy. Then you can do a common tangent, just like what we did in the tutorial and in the lecture. but just for fun, you can also do a Maxwell equal area construction. So the idea is actually plotting how the chemical potential changes with the psi bar. And now you are requesting the area under this mu psi bar curve across the coexistent density, and the area cancel out. So there's the other way you can find out what's the coexistent density for the BCC solid and the liquid, right? Okay, so that's the original PFC. Now that is adding the second mode, right? Because the first mode is 1 over root of 3, 1, 1, 1, so the magnitude is 1. And the second mode is 1 over root of 3 and 2, 0, 0. So the magnitude of that vector square, that would be 4/3, right? So that's why I'm putting the number here, okay? So I'm still using epsilon equal to 0.3, but the control parameter here that control the strength of the second mode, I'm setting that as 0.05. So still doing the same calculation. And now you see the red curve now has a lower energy than the green one, which means the FCC now is the ground state over a certain period, certain range of psi bar. And if you do the common tangent, now you can find the coexistent density for the liquid and the FCC solid. Okay. So here is the phase diagram that you can construct by setting R1 equal to 0.05, and you can do the same thing for different value of epsilon to find what is the coexistent density. Now you indeed have a wide range for this liquid FCC coexistence curve, and also you could have BCC if the psi bar is small. So even in this region, you can have a BCC FCC coexistence. And I think before there's a question regarding whether you can have like 3 different phases coexist. Then I think right at a certain point, you can actually see there's a possibility for 3 phases coexist, like BCC, FCC, liquid, right? Okay, so of course now we have FCC. You can set up different configurations. Certain feature I'm showing you here is that you can have a polycrystal. It's not really clear, but you can set up a system, then let the evolution run. You can have FCC polycrystal, and you can easily form a twin boundary and measure its energy, etc. Let me show you a couple more examples. For example, here I'm running a 2-mode FCC liquid coexistence simulation, but I'm rather choosing a larger epsilon, so I can see a very nice facet or step flow feature. So I'm actually adding some atom flow or putting more density in a liquid. So you are going to see the structure is growing, or more atom is growing, or is going to attach on the surface. So the figure on the left would be the cross-section view on the top layer, and the movie on the right will be the cross-section across the center layer of the FCC lattice. Right, so now you can have this cubic system in 3D FCC, and you are seeing all this step flow. So if you really look closely, you can easily verify that because that's the cross-section, right? So locally, you can see this atom here, they're forming a very nice square, right, with the atom in the center of that surface. But we are expecting the bottom layer, right, there should be only atomic position is shifted by half of lattice. So if you really closely, you look at that, indeed, it will be the center layer of that FCC structure. Okay? So that's the idea of the 2-mode. It's quite straightforward once you see that adding more building block, that is the second mode, it can stabilize the FCC structure. Once you understand that, you just implement that straightforwardly in your model. You can get a different structure.
So in 2D, this will produce a tetragon.
2D?
Rectangle.
2D, you can have a square lattice.
So here,
right,
because K0 and K1 are not equal, right?
Right. So in 2D, if we would like to have a square lattice, so we have 1, 0, 0, 1 as my principal residual lattice vector. So the next one should be square root of 2, which means 2, 0, 0, 2, right? So, in that case, and this should be 2, 4 actually, right? 1, no, I'm sorry, 1, 1. The second mode should be 1, 1. So the length should be square root of 2, and here I should put into 2. So it depends on different structure and different dimension. Pick the second mode, and there will be a corresponding. So this value should change with the dimension and also structure. Okay, so the idea is to adding more modes, right? So that brings us to very quickly, briefly, the work by Greenwood, right? So Greenwood actually have 2 papers. So it's also work from Prof's group. They show that basically you can include more detail from the structure factor or from the correlation function and to also get different structures. So the starting point is the classical density functional theory that we have been showing before, right? So the idea is that before we only consider the correlation function in the residual space is only around the first peak, then that's it. But if you want to consider different structures, like in 2D, if you would like to have a square lattice, or in 3D, for example, like simple cubic or FCC, the idea is not only to consider the first peak, but to add the second or third peak. You can include more and more peaks if you want to. So the C2, basically, they are, because if you want to have a proper description of this C of K, you need to assign what will be the height of each peak. And the other part will be how broaden or what will be the width of the Gaussian function, okay? So the way they're putting this is the correlation, the information is simply by this form. And it's a feature that if in real space, right, if you do an MD simulation, you know in your solid, the atom is going to fluctuate around. So if you do a tiny average sense, you are going to see the density profile of atom. There is a width like a Gaussian, right? But there is a broadened width. So if you assume the density profile can be described by a Gaussian profile, when you do the Fourier transform, the Fourier coefficient will also be a function of Gaussian. So that's why it is very nature to assume C2 also have this kind of information here, okay? All right, then because this part control basically you can say the curvature of each peak, and we sort of have shown that the curvature, right? We have shown that C double prime K actually control the interfacial width. So actually, it's a free parameter you can put in here for the different widths. Like for the first peak and second peak, they could share different widths, but that width will control the solid liquid interface width. Okay, so that's actually this part. So the rest of the story is about setting the proper height for each peak. So if you just run an MD simulation, you know when the temperature is close to melting or just let the temperature getting higher and higher, then you are expecting the correlation, the peak is going to decrease over time, right? Because now the entropic effect is getting more stronger than the enthalpy or the potential. So you can make the height of the peak as a function of this temperature. So you have several parameters here. I'm not going to go through a detail, but some of parameter is associated with temperature. So that describes when the temperature changes, the height of the peak will also drop or increase. And we also know when we do the derivation and for the different density wave, and there will be some coefficient associated with how many density wave you have. So there will be certain parameter associated with number of planes which correspond to number of residual lattice vector you are having, and also the atomic density of that plane you are describing. So this term they put in more phenomenological way, but that would give us or give the system more or less the same idea. You are including more building blocks, right? So for square lattice, you're just adding a second mode this way. Compared to a two-mode model, of course, you have only R1, it's easier to implement, right? But since you only have one parameters, then the shape of the structure factor, the degree you can control that is limited, but it's quite straightforward using the very, very simple idea. Here you have a more degree of freedom, but the idea still goes back to using more building blocks. So in the PRL paper, they have shown this phase diagram, okay? So you can have, here is like a liquid square and liquid triangle, and here is like a triangle square coexistence. So here they are choosing the parameter right here. Let me see if I can zoom that in. So you can have a triangle lattice, square lattice, and the liquid in coexist, right? But the idea basically is back to the multi-mode implementation. And for 3D, you can have, that's also zooming in again. And in 3D, you can have a liquid BCC and FCC here, right? So if you zoom in this part, you can have this BCC, FCC coexist, and liquid or BCC liquid, liquid BCC or liquid fluid, liquid FCC, depends on which parameter range you are choosing. Okay, so feel free to read those two papers if you would like to implement the what they call now the XPFC model, okay? But the idea is still consistent with this two-mode or multi-mode PFC model, that you will need more building blocks in order to have other structure than BCC in 3D. Okay, so that concludes the first part of this PFC model for other crystal structure. Basically, you can use more ingredients or more building blocks so that the BCC will not be the favorite phase always, all the time. Okay, the second part of this talk is that instead of using a multi-mode, either the XPFC or 2 modes or 3 modes, if you want to implement 3 modes, that's also straightforward here, just multiply by the other kernel. That's something we have done for FCC, and we compare the solid liquid behavior with a simple implementation, just taking the whole structure factor from the Perker CFA approximation. So here you can also do a multi-mode, because using the spectrum method is quite straightforward. You just keep multiplying the kernel, right, in your code, right? So in the spectrum method, the implementation of multi-mode model is quite straightforward. Okay, but let's talk about the other way. Is we know we can manipulate the second mode, right, or more modes, but we can also manipulate the nonlinear competition between density waves, right? So you can still go back to the single mode, but just saying, okay, instead of this quartic nonlinearity, you can adding like a zoo, a park. You can include all sorts of nonlinearity and to study how the nonlinearity affects the density wave competition. So that will be something I'm going to talk about now. So for example, if you consider a nonlinear term that's psi square times Laplacian to certain power and operate on psi square. So the simple case could be Laplacian and psi square and times psi square, or the Laplacian square and psi square, etc. So you can assume density waves, right? You can precise this summation all the density waves, and density wave can point out in different direction, because now we don't specify what would be the lattice symmetry. We're just saying you can have a rotational invariant. That's important. So your K factor can be in any orientation. So you plug in that insights and you do the integration. And for example, if you only pick up like 2 density waves, right? It's going to give you a lot of terms, but there will be 2 terms associated with the summation of the random selection of 2 peaks, and also the difference between those wave vectors. So, for example, if you have a K1 in this direction and K2 in this direction, and this kind of combination can be rewritten into the sum of them and the difference of them can be rewritten into the angle between K1 and K2, right? Just you have to do a little bit manipulation, but you can write the energy contribution from this kind of nonlinear term will have this contribution. Okay, but that's actually something quite informative, because when I adding something to my free energy functional, and the goal for this free energy functional is trying to minimize everything. But suppose I only have one set of building block, so which means I know Q is a constant, right? But now I have a term in the free energy that's the angle dependent. It depends on angle between K1 and K2. So which means for certain combination, the system might favor certain angles, which minimize the free energy of this contribution from this nonlinear term. So it could be 60 degree, it could be 90 degree, it could be anything. That would depend on the detail of this combination. So for example, if n equal to 2, then you can see if n equal to 2, if n equal to 1, that would be just cosine squared plus sine squared always equal to 1. So it does not depend on the angle. But if n equal to 2, you can see to minimize this term, then theta has to be pi over 2. So which means initially, if you set up a system with a tiny perturbation, which means the system doesn't have any preference in the very beginning, it's just according to the linear instability, all density wave with the magnitude equal to Q will be picked up. But now if they pick up two effector with the angle in between that's 90 degree, it's going to lower energy, right? So that mode is going to be enhanced. So in the end, in 2D, instead of having a triangle lattice, now you can have this square lattice because they favor to form wave numbers with the angle separated by 90 degree. All right, so now you see how the nonlinear terms or the nonlinear interaction actually dictates the interaction between mode, which means dictates the lattice symmetry. Okay? So in this 2010 paper, we actually consider combination of nonlinearity, but the concept is quite similar. Just one comment to this calculation is that you see you will start to pick up terms, right, in the free energy that depends on the orientation of those k factors. So if you keep the higher order correlation function in the density functional theory, do the expansion, you actually see those coefficients also depends on the information of the orientation of k. So those terms actually can be somehow mapped back to the density functional theory, especially to the higher order term, higher order correlation functions. So that's just the comment I would like to point out. Okay, so we did something, but we way back, but just for fun. So we didn't actually dig anything deeper, just trying to convince people that you can have certain nonlinear combination to get anything you like. So for silicon, we know it's a diamond cubic structure, right? So there's a reason why I'm choosing specifically this combination. Like you have a Perside to the quartic power and also gradient Perside also to the quartic power. But just let me skip the detail, but from the previous calculation, you probably get a sense why the nonlinear term can have certain preferred combination of k factor in the reciprocal space. So here's a calculation just to calculate for different combination of G1 and G2, what would be the ground state structure. So for example, at this region, you can have stripe phase, which does not correspond to anything realistic in crystal. But in this red region, you can have a diamond cubic, right? And in this gray region, you can have a simple cubic. And in the blue region, you can have FCC, etc. So here, just to show you, if you pick a parameter here, run a 3D simulation, and that's actually an iso density plot from a PFC simulation. So here I just mark, because diamond cubic would be a combination of two FC structure, but with the second FC structure shifting along the diagonal by quarter of the lattice spacing, right? So I'm specifically marking the two FC structure with different colors. But the idea is that you can use the nonlinearity to control or to design the desired structure that you like. And sometimes it could be fun because you can just do a simple manipulation to get something like this, right? So layer specifically can actually see how the density wave interact and how they favor to form different angles. So here's a 2D calculation. But in 3D, actually, you can actually see why they like to form this tetrahedral bonding like this, okay? So that's pretty much what I would like to share with you about the PFC model for different crystal structure. The idea always goes back to either adding more building blocks, like including a second, third mode, etc. I think the advantage of that is basically similar to why we would like to truncate the density functional theory to the pair correlation function, right? You capture a certain nice physics, and it's easy to implement. But I think it's also important to know that you can control the nonlinearity to obtain the structure that you like. And in theory, you can connect the nonlinear term with the higher order correlation function, and that's something that will be interesting to work out as well, right? Okay, yes?
That is the functions of Texas house. There is actually 3D space of the
Oh, yeah. That's right. So you are saying there should be also a function of loss parameter, right? That's right. Yeah, I think in this calculation, I'm fixing epsilon to a certain value. I'm not showing it here, but you are right. It should be a higher dimension space. So maybe along the plane into the screen, all the color region will also have different changes. But that's right. Yeah. And also, I think I'm fixing the mean density as well. Yeah, so actually it's a higher dimensional phase diagram.
It is a generalized function of generalized hierarchy. You can get any.
I mean, so far I've seen people proposing either the multimode model. Mostly, I think multimode you can have HCP, FCC, of course BCC in 3D. Diamond cubic, rarely, or even maybe one paper, but in 3D structure, pretty much you can get everything using the multimode model. Yeah, but diamond cubic, I think there's one. I have to check. Yeah. It's very challenging to get a diamond cubic. Here, I'm showing you here, I can have a stable diamond cubic solid, but I couldn't get the diamond cubic solid liquid. Yeah, I mean, there's some details. Is that for G1 at this region, you can only have a stable solid. You have to move to the other side. Yeah, but that's something. I mean, would be interesting to work out because diamond cubic is something. It's an important structure, right? So silicon is diamond cubic. So, yeah.
Some epsilon psi bar combination you expect that the diamond cubic will be in contact with liquid?
There's a reason here I didn't show, but just with those two nonlinearity, you will not be able to get solid liquid, diamond cubic liquid. No. Yeah. But the calculation I bring it's quite a long time ago. So I suspect there should be a way to get around with it. All right, so just think about either the multimode or nonlinearity, and maybe something that we can work out in a tutorial session tomorrow. I think maybe something like a two-mode FCC or XPFC model working, applying to how we can get HCP, for example, from this XPFC model. That is something we can also work out tomorrow. All right.